All right, ladies and gentlemen, we have reached the end of thermochemistry. We are talking about Gibbs free energy today. And I would say that you will 100% see a Gibbs free energy calculation / question on the FRQ section. 100%. Now, the problem is that the Gibbs free energy equation deals with three separate topics. It deals with thermochemistry, it deals with equilibrium, and it deals with electrochemistry. And so we have just hit the first cycle of Gibbs free energy. It will come back again. I have a little deja vu when we talk about equilibrium, and I'll have a little more deja vu when we talk about electrochemistry. So just be aware, keep it stuck up there, that we will be seeing this several times. And on your equation sheet for the exam, you'll see the equation several times. We will get into that at some point. But we're going to wrap it up and tie it all together in a nice little bow for thermochemistry, and then we are moving on. So what Gibbs free energy is the energy available to do useful work, like run a car engine or heat a house or those kinds of things. Basically, it's energy that's available to do something useful. And when we talk about Gibbs free energy, it's represented by a capital letter G. Finally, a letter that makes sense, right? Gibbs free energy is a capital G. It is measured in kilojoules because it is an energy value. We typically see it in kilojoules or kilojoules per mole. And Gibbs free energy, the reason why we use it so many times is because it's an indicator of something that we call spontaneity in chemistry. And spontaneity is a chemical process that happens on its own, unassisted by energy constantly being pumped into it. So if you think about rusting a car will over time spontaneously rust. It'll get rust on it. It's not a fast process, but it does happen unassisted. If something happens spontaneously, it happens unassisted, just on its own, like melting ice or something like that. If something is non-spontaneous, it means that you need to help it all along the way to make that process happen. And Gibbs free energy and the sign of Gibbs free energy indicates whether a process is spontaneous or not. Now, the College Board is moving away from the term spontaneous, but you do see it sometimes. What they like to do is they like to use the term product favored. So a product favored process is something that happens spontaneously because it naturally heads to products, if you think about it. So product favored means that at this specific temperature, it will head to products eventually. If a process is reactant favored, it means that it wants to stay as reactants at that specific temperature. And here's the big thing. When we talk about Gibbs free energy, a product favored or spontaneous process has a negative Gibbs free energy, which means that it gives energy out at the end that it can do useful work. So if it gives out energy, it's got that negative Gibbs value, and that means it's either going to be product favored or spontaneous, as we call it. Okay. Now, the bigger the negative value or the more negative it gets, the more product favored it is. So if we get huge negative G values, it's going to be a big product favored reaction, which means you're going to get a lot of product and not much reactant left. If you see a Gibbs free energy value around 0, it means that you kind of have this teetering between product favored and reactant favored. And if I have a positive Gibbs free energy, it means it's reactant favored. And Gibbs free energy is kind of fluid depending on the specific type of reaction that happens. So we're going to dive into that because it's really important. And I would say the math with Gibbs free energy is something that they're definitely going to hit on the exam. Now, of course, there is a products minus reactants equation for Gibbs free energy as well. So they could give you a whole table of Gibbs free energy values and you could find the Gibbs free energy. You don't see that very often on the exam. And at this point, I'm not going to go over any examples because you know how to do these, hopefully. Okay. And if you don't, go back to the entropy and enthalpy values of formation, and then you can look at those practice problems. Here is the big guy, though, that you need to know for thermodynamics, and it's delta G equals delta H minus T delta S. G being Gibbs free energy, measured in kilojoules per mole most of the time. H is enthalpy, we know that, also in kilojoules. And then it's minus T, temperature, and temperature is going to be in Kelvin 99% of the time. And then entropy is in joules per mole Kelvin. So what happens is every chemical process has two parts that drive its spontaneity or product favoredness. It's its entropy and its enthalpy value. So the H and the S. Entropy is S, H is enthalpy. Both of those things drive the G value overall in this equation. And so what you can kind of think of it as is I've got an enthalpy component that could be supported by the change in entropy or hindered by the change in entropy. And that's what they're really going to ask you to figure out. And it's more an issue of, do you understand the chemical processes and do you understand how they tie together in the math? I'm going to give you guys a table to start off with here, and then we're going to walk through each of the situations. So if I have a negative entropy, negative enthalpy and negative entropy, my reaction is going to be spontaneous or product favored at low temperatures. If I have a positive enthalpy and a negative entropy, that can never be product favored ever. Like, it's just not going to happen. Positive entropy and a negative enthalpy means that that reaction will happen no matter what temperature. And if we have a positive enthalpy and a positive entropy, spontaneous at high temperatures. And we'll dig into this. As I've kind of said before, the best possible scenario is to have an exothermic process, because nature likes to drop in energy, and to have more dispersion happen. And if you look at this equation and think about it as kind of competing positive and negative values. If I have an exothermic reaction and a negative value here and a positive value for my S, that makes the term where I take temperature and entropy, it makes this whole term here a negative value when I'm subtracting it. So I guess I should say it keeps the temperature and entropy value positive, so it's negative and I'm pulling it out. And what ends up happening is that if I have a negative entropy and then I'm subtracting a positive number, so I'm subtracting more, that's going to make it so that my Gibbs free energy is always negative. And it's always product favored no matter what. So the best possible conditions for spontaneity or product favoredness are going to be a negative enthalpy and a positive entropy. Okay. All right. Different scenario now. And let's see if you can kind of parse this out. If I have a positive enthalpy value and a positive entropy value, to be product favored or spontaneous, want a negative Gibbs free energy. So right now, my enthalpy is working against me. But positive changes in entropy are good. So if I can get this term big enough, it can overtake enthalpy as the main driver for my spontaneity. So when I have a positive entropy value, this whole term here becomes a negative, I'm subtracting it, then it's going to be product favored when the temperature is high enough. So if this half of our reaction is negative enough because the temp is high enough, I can get a product favored reaction. Okay, here's another one. Enthalpy is negative, so we're exothermic. That's good. But entropy is negative as well, so it means we're getting less dispersed. So if we think this out, and enthalpy, lots of similar sounding terms here. Enthalpy is negative, but because S is negative, this whole term becomes a positive. So I have a negative, and then I'm adding something to it. What'll happen is as the temperature goes up, eventually this term will make my enthalpy's contribution not matter. So what happens is I got to keep the temperature low enough so that my entropy effect on Gibbs free energy does not overtake my enthalpy effect. So think about enthalpy is negative, but what ends up happening is if the term on the S gets big enough, it will become positive overall and it'll make it not spontaneous or reactant favored. And then lastly is our situation where I have a positive enthalpy value and then a negative entropy value. So it's endothermic and it's getting less dispersed. In that situation, I have a positive term for the right half of my equation, and then I have a positive term for the left half. And so in that scenario, it's never product favored ever, because it's always going to be a positive value. This is what I call math logic. And this math logic is something they're going to test you on all the time. They could also test you on the algebra of this as well. So we're going to go through a couple different examples where I can show you the math logic argument, and then I'm going to show you a little bit of math with it. Okay, so my first example is, again, an old AP exam question, and it gives you this reaction here, and then it says, in thermodynamic terms, a reaction can be driven by enthalpy, entropy, or both. So that's what I'm saying. The entropy is good, the enthalpy is good, or both of them can be good, or it'll hinder it. So considering that the flask gets cooler as the reaction proceeds, what drives the chemical reaction? Answer by drawing a circle around one of the choices. That's the first part. And then you're going to justify your selection in terms of Gibbs free energy. So they're kind of leading you there to talk about Gibbs free energy at some point. They're like, hey, you probably want to think about Gibbs free energy. So we're going to take a look at this. Now, there are some context clues here. It's telling enthalpy and entropy. So that means we are going to have to think about our equation, delta G is equal to delta H minus T delta S. And so we're going to have to read through this problem and figure out some context clues about what the heck's going on. So if we look here, it tells us that the flask gets cooler. So if you think about it, it's getting colder to the touch. We know at this point, hopefully, that that's an endothermic process if it feels colder. So that means that it is a positive enthalpy value, which means right away we know that the Gibbs free energy is not being affected by the enthalpy. So we can knock that one out. Okay, now we'll check entropy. If we look here, we're going from a solid, an aqueous, to aqueous, a liquid, and a gas. So that is already increasing our entropy. And we're also going from 2 moles of stuff to 3 moles of stuff. So we have a positive entropy value, which is what we want. So in this case, we know that the enthalpy isn't helping us because it's endothermic, but this is. So our correct answer is going to be entropy. And then it says to justify your selection. So what we need to do is kind of discuss this math without actually doing any number calculations. And that can be kind of tricky. So explaining your math logic is kind of tricky. So what it says is, since the reaction proceeds, which means it's kind of happening on its own, that means delta G must be negative. Okay, so we're right away clarifying that Gibbs free energy is negative. Then I'm going to say the cool flask means the reaction is endothermic. With a positive delta H. Okay. This means H does not contribute to a negative Gibbs free energy. Okay, so I've kind of explained why I knocked out the enthalpy component. Then, because delta G is negative, okay, so because delta G is negative and entropy is positive, I think it would not hurt to kind of drive back here to this reaction because it produces more moles. The S contributes to the delta G driving the reaction. And I would say explaining that math logic is probably a little bit trickier than actually just doing the math, which would be, convenient. So that's kind of annoying, but that's okay. All right. So the next one then. Oops, excuse me here. So it says that a student reads in a reference that NO and NO2 will react as represented by the equation below. Thermodynamic data are given in the table below for the equation. It says the student hypothesizes that increasing the temperature will increase the amount of N2O3 in the equilibrium mixture. Now, technically, we haven't talked about equilibrium, but it shouldn't matter as long as we can look at the reaction and kind of pay attention. So it says indicate whether you agree or disagree with the hypothesis and justify your answer. So what it's saying is that if I make T go up, I am going to make this N2O3 go up, which means that I should get more product. Okay, and I've talked to you before that if that's the case, it means that we are going to make our delta G more negative. So this is another math logic problem that we've got to kind of sort out here. So what it's saying is that if I increase the temperature, I should have a situation where the values are going to be becoming more product favored. So it's time to go back to our equation. Delta G equals delta H minus T delta S. So if I look at that and I look at my data that I have here, I have a negative enthalpy value and I have a negative entropy value. Okay, so if I look at this, currently negative, if I increase the temperature in this scenario, I make this term more positive, right? Because this currently is a negative minus a negative. So if I make this term bigger, eventually what's going to happen is I'm going to surpass the point where this negative from the enthalpy matters, and I'm going to become more reactant favored. So this is not correct. So what they're saying is that I'm making more product, but in this case, as T goes up, my delta G actually becomes more positive, and so it's the opposite. So what we need to do is answer the question, first of all. We're going to disagree with them and then justify our answer. So we're going to disagree, okay? Then we're going to say, as delta T increases, delta G becomes more positive, making less product. Okay. Now, in this case, I think this is a sufficient enough explanation if you have this equation here. So you've got kind of the math logic going here. So if you wanted to beef this answer up a little bit, you could say, as T increases, the effect of entropy will be greater making delta G more positive. So you could bring that in as well, and that would be something to kind of consider. But a lot of times they want to see, can you do the math without actually doing the math? However, if you have to do the math, you can do that as well. So if we take a look here, we've got a reaction, and they give us the H and the S. So if they give you both of those, there's a good chance you're doing a Gibbs calculation. Because the dehydration is not observed to occur at 298, the student claims the reaction has an equilibrium constant less than 1. In this case, we haven't talked about equilibrium, and I forgot to change this. So we'll say the reaction is, we'll say, not product favored. Nothing like winging it here, guys. So we'll say that the student claims the reaction is not product favored. Do the thermodynamic data support the student's claim? Justify your answer, including a calculation. So in this case, we got a calculation here that we can kind of get rolling with. So we've got delta G equals delta H minus T delta S. So we're going to do a little bit of math here. We're looking for Gibbs. So we have our enthalpy value of 45.5 kilojoules per mole minus our temp. Now it tells us it's at 298. So 298 Kelvin times our entropy. But remember, this is in different units here. So I've got to convert to kilojoules, dividing by 1,000. So it's 0.126 kilojoules per mole Kelvin. Now, see, the nice thing here is that the Kelvin cancel out, and then we're left in kilojoules per mole and kilojoules per mole. So if I take those numbers and I do the math, I do the multiplication, and then I subtract the two, I get a value of 7.95 kilojoules per mole for my Gibbs free energy. So I've done the calculation for the support. So what I need to do now is, in this case, I'm saying it's not product favored. The reason why this says equilibrium constant is because, like I said, it ties it back together. So we'll get into that when we get into equilibrium. But anyways, we'll say it's not product favored. Do we agree with that? In this case, we would say it does support it. So it does support the fact that the reaction is not product favored. Because delta G is positive. And that's all you need to say. A positive Gibbs free energy means the reaction is not product favored. And that's it. So that's all we've got to do. So we're going to talk about these a little bit more when you get to class. If you have any questions, please make sure you get them cleared up, and then we're going to take a crack at your homework. So if you don't have any questions, good luck.